We'll be looking at the technique called differentiation or derivation, which is a technique to find what we call the gradient function. So we worked with the notion that all linear functions have a gradient, which is a constant that we use. We call it m, or we call it a, depending on your preference. So now we're going to introduce the concept of a not a gradient, but a gradient function, which applies to all functions, not just linear ones. So if we have a function called y and it's equal to 2, so this is a function y equals 2. Now if we wanted to find the gradient of that, we could take a look at what y would look like. So I can draw it on the side here, and y equals 2 would look like this. So it's a straight horizontal line breaking the second axis at the point 0, 2. This line doesn't rise, so it's fair to assume that it has a gradient of 0. Now, if we consider the function y equals 2x plus 1, we could draw that too. It would, let's see, yeah, it was easier to paste in a straight line there. So it would look like this, and if we wanted to find the gradient would be 2. So 1x to the right and then 2y up, right? And we could also identify the gradient by, we know that this expression here identifies the gradient as this number here before the x. So that applies to linear functions. Now we can arrive at a formula for transforming a function into its gradient function. So one of these systems, or the way to write it, they were both invented independently by Leibniz in Germany and Isaac Newton in England. And I think it's fascinating that they actually discovered this more or less at the same time, independently of each other. So it's a very powerful result. So Leibniz, if he had a function that he would use the letter y, and if this was a power function like this, then this would be the function, and the gradient function, he would find this by using this notation here, dy over dx. It's not a division sign though, it's not a fraction per se. And then nax to the power of n minus 1. So this is the notation. I'll explain how it works afterwards. Now Newton would use this notation here, f of x, where x is the variable. So if this is the function, then he would find the gradient function by using this notation. But the method is the same, so there's a difference in notation. Now, you may note that, okay, I'll just put a circle around this. Yeah, so this is important. Now, you may note that this dy dx thing, it's a bit like this delta y delta x that we've used to find the gradient. And it shows that this is about changes in function value in relation to changes in the variable. And that's exactly how we found the gradient for straight lines. And now we can also apply this to curves. The gradient function measures rate of change. We can say that for a graph y equals f of x, the gradient function dy dx, or if you like, f derived of x, gives the rate of change of y with respect to x. Like this. So we're going to have a look at a couple of examples, and we'll start with the two we've just looked at. So if we want to differentiate the function y equals 2, we can do that. In this case, if we were to write it on the same form as a polynomial, then this would be 2x to the power of 0. Because x to the power of 0 is 1, so 2 times 1 is 2. So this is the same thing. We can identify our, put that in a different color, our a is 2, and our n is 0. And when we want to find the gradient function, we take dy dx, and we take n multiplied with a, and then x to the power of n minus 1. So differentiating this function means that, okay, we take dy dx equals 0 times 2 times x to the power of 0 minus 1, that's n minus 1. And this, well, no matter how you don't have to think very hard on this, because you have 0 multiplied with something, so that's always 0. If we want to differentiate the other function, and now I'll just use the other notation just to show you, f of x equals 2x plus 1. And our function then is, we could just as well write this as 2x to the power of 1 plus 1, because x to the power of 1 is x. Now, for polynomials, we need to make sure that we differentiate one term at a time. So we need to deal with 2x to the power of 1 first, and then 1 afterwards. And now we have a equals 2, and the n is 1 this time, it's not 0. So now we want to find, I'll put it under here, f derived of x equals 1, because we want the n first, and then multiplied with 2, multiplied with x to the power of 1 minus 1. And that's the first term. And the second term is a constant. And we saw in the previous example that any constant is going to be 0 when we differentiate it. So we have plus 0 at the end. And again, so f derived of x equals, 2 multiplied with x to the power of 0, which is 2 multiplied with 1, which is 2. And that's the same result as we already know how to find. So the gradient of a constant function is always 0, and the gradient of a linear function is the same number as we put in front of the x. So maybe 2 more examples. We have the function y equals 3x to the power of 4. We want to differentiate this dy dx. We need to take the n, which is 4, multiply that with 3x, and then to the power of 4 minus 1, which is going to be 12x to the power of 3. Slightly more tricky example. Here we have y equals 2 divided by x plus x. So here we have to do a little bit of rewriting perhaps before we begin, because this is, 2 divided by x is 2 divided by x to the power of 1, remember. If we multiply with x to the power of negative 1 upstairs and downstairs, then we get 2x to the power of negative 1 and then just 1 underneath, so we don't have to write that, plus x. So this is just a rewriting of the same function. If we want to differentiate this, dy dx equals negative 1 multiplied with 2x to the power of minus 1 minus 1 plus x. Now the derivative of x is just going to be 1. You can apply the formula and check. Our first term is then going to be minus 2x to the power of negative 2. And then we have to add plus 1. There's an alternative way to write this as well. If we want to go back to our starting point, we could write minus 2 divided by x squared.